Okay, in this video, we're going to look at something a little bit, well, sort of a little bit different. It's actually totally connected to what you guys have been taking with electric fields and charges and that type of stuff, but just a kind of a different aspect of it. We're going to look at what are called Gauss's laws for electrostatics, electrofields, and that type of stuff. Now, basically what Gauss worked on was like electrostatics, electric fields, and basically the stuff you guys are working on. But what this has to do, well, the way I like to think about it is usable field, whether it's electric field, magnetic fields. When I think about this type of stuff, I think about usable fields. And a quantity that comes up with this is what's called flux. And I'm sure, this is usually where the jokes come out about the flux capacitor from Back to the Future, but you guys are getting kind of young for that. That was a long time ago when that movie came out. But the idea of flux is what kind of field is actually usable. And the symbol for flux is the Greek letter phi. I'll clean that up a little bit. The Greek letter phi is the symbol for flux. And there's different types of flux. There's electric flux, there's magnetic flux. Whenever you have a field, you can talk about flux. And we're going to look at a couple things about Gauss's laws and how flux actually works and that type of stuff. And he had some different laws or rules for this type of thing. And one of the things that he said about this type of thing is if you want to talk about flux and making it usable, he said, first of all, like the net flux, or the net flux, whatever you want to call it, into the symbol, is directly proportional to the enclosed charge. So we can look at that a little bit. Now, to analyze this type of thing, we have what are imaginary surfaces. And they're often called Gaussian surfaces, and they're imaginary surfaces, and that's what these purple and green little ovally type things are. They're called Gaussian surfaces. They're imaginary surfaces to analyze what's happening inside. And if we sort of look at them, we can sort of analyze this whole net flux is directly proportional to enclosed charge type idea. So if I look at surface A, there's a whole bunch of charges inside of A. I've got 1, 2, 3, 4 negatives. I've got 1, 2, 3 positives, but that's a double positive. So I've got -4 and I've got +4 altogether, which means the net charge inside is 0. The enclosed charge inside of A is 0. So since I've got like 0 net charge inside, there is 0 net flux. The flux isn't good for anything. Every time a flux goes out from a positive, it's going to go into a negative. It's not going to do anything. So I can't actually use Gaussian surface A or the charge inside of A to do anything because everything cancels out. If I do the same thing for B, just for B here, I've got a negative and a positive, so they cancel out, but I'd be left with this guy right here. So the charge for that guy would be +2. Which means I could actually do something. If I took the charge enclosed inside of B, I could actually do something with it. Okay, for C, there's nothing inside of C. There's no charges. Now, that doesn't mean there's no field going through it. Like, for example, field would go from this positive, it would go through it and hit the negative, but the field goes in and the field goes out. There's nothing there. So I can't use C for anything either. And if I did for D, let's see, D's got, over here, got 1, 2, 3 negatives. I've got 2 positives, so +2 - 3. I get a net charge of -1. So it would also be usable. So B is usable. That's okay. I could use this one. D is usable. I could do something with that one, like apply forces or something like that to it. And B would be 2 times as useful because the net charge was twice as much as D. So that's the basic idea behind the first law for me is the charge inside, the net charge inside dictates the net flux. B would have twice the flux that D does. A and C have no net flux. They're totally useless. Okay, so that's one part of Gauss's laws that he worked with. Okay, so now let's look at another aspect of it. Okay, so here's a second picture, and for some reason there's some kind of weird plus sign thing in the middle. I don't know if I can sort of scribble that out a little. That's not too bad, actually. All right, so what this is a piece of metal. That's what this is. So this thing right here, that's a piece of metal. And the other thing that Gauss said about how this type of stuff works is if you have any kind of conductor, he said that any extra or excess charge goes to the outside. Okay, so if this is a piece of metal conductor and you put a bunch of positives on it, the positive charge would all go towards the outside because, of course, they're repelling from each other and they would go as far away as they possibly can from each other and they'd all go to the outside. And not only that, because of this, the electric field inside is equal to 0. All the electric fields inside of here would actually cancel out. So there's no electric field or no net electric field. We should put net on here. Let's be a little more better. The electric field, the net electric field inside of a conductor is going to be 0. Everything cancels out. Not that fields don't exist, but they're going to be 0. So if you could magically make like a little Gaussian surface just on the inside of this conductor, just inside the surface of the conductor, the electric field is 0. There's 0 net charge. There's nothing. You've got absolutely nothing to work with. But if you would take that surface and just go to the outside of the piece of metal, now you'd have a huge enclosed charge and you can actually do something with it. So that's the slight difference between being inside a conductor and outside a conductor. Now, this is the idea of why it is safe when you have conductors and stuff like that that have electricity going through them. So here you are in here, there you are, okay? Okay, there you are inside the conductor. You are perfectly safe inside of that conductor because of Gauss's law, extra charge stays on the outside and you are not going to have any forces or anything happen to you. This is why if you have a car that crashes into like a telephone post or something like that, or a hydro wire, and the wire hits the car and the wire is electrocuting the car, you're perfectly safe inside the car because all the extra charge and all that kind of stuff is going to stay on the outside of the metal shell of the car. So as long as you're inside the car, you're perfectly safe. Now, of course, if you go outside the car, then you're not safe because you are now outside of the enclosed conducting area. You can be then interacted with by the electric field and all that kind of stuff. Then it's not going to work out well for you. So the safest place to be is inside a metal conductor, and nothing's going to happen to you if there's electricity involved. Okay, so that's another application and idea for Gauss's laws. Okay, so now I'm going to show you a third thing that has to do with interaction, because in order to use electric fields, in order to apply electric fields to cause forces and actually do stuff with them, you need to interact with them and have usable flux and usable field that you want to use. So I'm going to show you another set of pictures that helps to show that idea. All right, so here's the last picture I'm going to show you involving Gauss's laws and that type of stuff and how to actually have flux and usable flux. This picture is actually taken from one of my university textbooks, and yes, believe it or not, I actually did go to university and I did take physics university and I actually passed physics university. So hey, what do you know? Anyway, now this sort of shows the idea of how to actually calculate how much flux you can actually use. And the best way I can think about this is to think of a sailboat and wind and a sailboat. So here's my little sailboat picture, and this is my favorite way to think about how this works and all that kind of stuff. And basically, if you want to actually use field, it's just like wind for a sailboat. The key to the whole thing is you have to interact with it. And the more you interact with the wind and how you interact with the wind dictates how a sailboat will actually work. Well, same thing for flux. There's no difference. So we got that first picture here, picture A over here. You got this area. It's just imaginary area in an electric field, and there's interaction going on. So you could actually do something with it. And it sort of shows the different factors that kick in that actually can increase or decrease the amount of interaction you get. For example, here, if you use a larger area, you will get more interaction. There's going to be more flux. There's more stuff you can actually do. The same way if you've got a bigger sail, it's going to work better for a sailboat. The same thing applies for picture C, a larger field, a larger flux. So if the electric field becomes stronger, like having more wind, you can do more stuff with it. And the bottom two pictures here, this is about the orientation. It's the angle that is important. Just like for a sailboat, you will angle a sail in different ways in order to get different effects and different amounts of interactions. So these are the three things that are actually used to calculate flux. Like now the actual formula for flux, for electrical flux looks like this, EA cos theta. And that's how you can calculate how much flux you can actually use. And the more field you interact with, the better the forces are, the better everything with any type of electrical, anything that's actually out there. And this is the basic idea of how it works. So obviously the stronger the field, the more interaction, the more flux you have to work with. The bigger the sail, the bigger the area, the more you can work with. That also improves how much flux you have, how much useful flux you actually have. The tricky part, so to speak, is the angle part, because it's E cos theta. Now, the thing is, if you look at, I want to expand on this a little bit because this is where, well, you guys would call it tricky, that whole cos theta thing. So, for example, here, that looks like 90 degrees. Between the area and the field is 90 degrees. But the cos of 90 degrees is 0, which means the flux would be 0. This does not look like a 0 flux. The same way here, the angle between the two things is 0 degrees. The cos of 0 is 1, which maximizes the flux, but this doesn't look like maximum flux. Now that's because that is not the angle we need to be using, okay? The angle isn't measured between the electric field and the area the way it's pictured here. This angle right here is actually measured between the electric field and the normal of the area. Okay, so areas actually have a vector that comes out of them, and I'm going to draw it here. Let's use that color. We'll do this one first. The vector for the area actually comes out at 90 degrees to the area. It's like the direction for the actual area calculation. And that is the angle that or the vector that you use to actually measure the angle. So the angle between this vector and the electric field is 9 degrees. And cos of 90 degrees, of course, is 0, and that's why this one right here has 0 flux. If I go back over here, the normal vector would come out of the area something like this. The angle between the area normal vector, the normal vector right here, and the magnetic field, the electric field is 0. The cos of 0 is 1, and this is maximum flux going through there. So that's where it's got to be a little bit, you got to be careful, is the angles between the field and the normal to the area, not between the field and the actual area. And there's nerdy math reasons where this comes from, but we're not going to worry about that. Same thing for this one here. This one would have a normal vector coming out here, and that angle would be measured something like this. Now, if you're not sure, especially if it's an angle like this one, if you're not sure which angle to use, the best piece of advice I can give you is think about maximizing or minimizing. That's the best way you can think about it. Just look at the picture, look at the setup, look at the angle. Is the orientation set up for more like maximum flux or minimum flux? Is it closer to maximum flux or minimum flux? And once you figure that out, just use the angle that's going to give you that type of value. If you have a very, very flat area, maybe not quite as flat as this one, but almost as flat, and you see little 10 degrees, you're not sure if you should use the 10 degrees or the 80 degrees. You're not sure which one to use. Well, just look at the picture. If it would be similar to this picture right here, that's closer to minimum flux. Well, what's smaller, cos of 10 degrees or cos of 80 degrees? Well, cos of 80 is way smaller than the cos of 10, so then use the 80 degrees. So sometimes just look at the picture, think about maximizing the function and minimizing the function, which is a really important mindset for stuff, especially university and stuff like that, and then figure it that way. Okay, so that's the idea how to calculate electric flux and the idea of how electric flux works and stuff like that. We're not actually going to do anything really with this expression. We're going to build on that when we actually get to magnetic fields, but it just gives you a little more background idea of how flux works and how they make electric fields more usable and where the term flux actually comes from and what Gauss's law actually means to apply to electrostatics and electric fields.